Alright, so now that we know how to represent or how to calculate the number of subatomic particles in an atom, the protons, neutrons, and electrons, we're going to take a look now at how we represent those numbers, in addition to one of the properties of the elements on the table, on the periodic table, which is oftentimes you find them being, or they exist as a mixture of what are known as isotopes. So the first thing that we need to do is to define what an isotope actually is. And we can define an isotope as different forms of the same element or we can say atoms of the same element that have the same atomic number but different number of neutrons. Right, so the key thing here is that these are just different atoms of the same element, right? That means that they're going to have the same atomic number or number of protons, but the number of neutrons are different, which would make the mass number different for each of those isotopes. And we have here an example of 3 of the isotopes of magnesium represented here. And the way that we represent isotopes is by using a particular notation called the atomic or the nuclear symbol. So when we write an atomic or nuclear symbol, it's always going to follow the following format. So it's going to look generally like this. We're going to have X, which is going to be our symbol for the element. And then as a superscript, we're going to have a number which will designate A, and this here is going to be our mass number. And then as a subscript preceding the element, we're going to have a number which will designate Z, and this here is going to be the atomic number. All right, remember the atomic number is also just simply the number of protons, and the mass number is just the sum of the protons and neutrons. All right, so this type of notation is what we're going to see. It's called an atomic or nuclear symbol to represent a particular isotope or a specific isotope for one element, which is one specific atom for that element. So the example that we see here underneath is for magnesium, right? So Mg is the symbol, and then the atomic number 12 down here tells us that we have 12 protons, and then the 24 is the mass number. This is the sum of the protons and the neutrons. Right, so if we have 12 protons, then in order for the mass number to be 24, then we're also going to have 12 neutrons, right? The number of neutrons is just simply, as we saw this in the previous section, the number of neutrons is the mass number minus the number of protons. Right, so this is a shortcut way to represent a particular isotope of an element. And again, an isotope is just an atom of the element, or isotopes are atoms of the element that have the same atomic number, but the number of neutrons are different. So for instance, we have 3 isotopes of carbon, which we designate as follows: C12, C13, C14. we're going to write the atomic symbol for each of those and then calculate the number of each of the subatomic particles. So when we write the nuclear symbol, that looks like this. There's a couple other ways that we can represent it to be a little bit more concise. All right, so this particular isotope of magnesium here, I'm going to just redraw this over on this side. So I have 24 Mg and then 12. This is also, or can be also written as magnesium 24, right? So we have the name and then the mass number, or we can write the symbol Mg24, right? These are just shortcuts to represent a particular isotope. So when we see C12, right, that is telling us it's carbon, and then the 12 here tells us the mass number. All right, so for each of these isotopes, for carbon, the symbol is going to be C. So we're going to have C, another C, and then a third one. All right, the difference between them is the mass number. So for the third one, we can say that's our C14, so the mass number is 14. The second one is C13, so we'll put 13 on top. And then the first one there was our C12, and that's in purple. So that's the mass number. It's different for all of them, but the thing that's the same is the number of protons, which is just the atomic number, and that's 6 for each of these, right? So that's how they're similar. They have the same number of protons in each case. So the one on the bottom is going to have 6 protons. It's an atom, which means the number of electrons is going to be the same. The number of neutrons is simply the mass number minus the atomic number, which would give 8 neutrons. For the yellow one, all right, again, we're going to have 6 protons, same number of electrons. Our neutrons now would be the mass number minus the number of protons, which would be give us 7 neutrons. And then for the first one, we still are going to have 6 protons and 6 electrons. Number of neutrons then, mass number minus the number of protons, which would be 6 neutrons. All right, so when you look at it, you take a step back and look at it, yes, there's a little bit of math involved, but it really isn't that complicated, right? It's just a little bit of subtraction and addition that we're doing. Okay, so we can we can go in the other direction, and we can, if we know what the number of subatomic particles are, we can actually generate the atomic symbol for each of these. So let's do the first one, and you can do the second one on the third one on your own. All right, so let's say that we had an atom with 8 protons, 8 neutrons, and 8 electrons. So the number of protons, remember, defines the element, tells us what that element is, and we can just simply look that up on the periodic table. And if we look up 8 protons, which is the atomic number, that's equal to oxygen, right? So we know then that this is going to be O. We have 8 protons, so that's going to be our symbol or our number down here on the bottom. And then the mass number on top is the protons plus the neutrons, right? Which is 8 protons plus 8 neutrons, which is equal to 16. And then that is our mass number that goes on top. So that'll be the atomic or the nuclear symbol for that first one. All right, and another way this question could be posed, so we're given 3 choices here, A, B, and C, and then we need to answer the question. So which of the pairs are isotopes of the same element? Right, so remember, isotopes have, or they should have, the same atomic number or number of protons. And in our nuclear symbol, that is represented by the subscript over here. So that's what we're going to look at to compare these, to see which pair has the same number of protons, and obviously that is going to be B, right? Because they both have 6 protons in this case. Their atomic number is 6. And then we can do a little bit of calculation to see in which pairs do both atoms have 8 neutrons. Well, to calculate the number of neutrons in each of these, right, we just take the mass number, which is a number on top, and we subtract the atomic number, which is a number underneath. Right, so this one here on the right would have 8 neutrons. This one here is also going to have 8 neutrons. All right, 15 minus 7 gives us 8. 16 minus 8 gives us 8. This one here is going to have 8 neutrons. 14 minus 6. 12 minus 6 is going to give us 6 neutrons for that one. And then for the combination in A here, or the pair in A, 15 minus 7 is 8. 15 minus 8 is actually 7. So the only pair that has both, where both of them have 8 neutrons, would be this one, C. All right, so again, a little bit of math involved, but it's not the most complicated math. All right, so we've seen how the nuclear symbol or the atomic symbol can be used to represent the number of subatomic particles in a concise way. One thing to keep in mind is that the nuclear or atomic symbol, right, that particular notation, is not what you see on the periodic table, right? So when you look at the periodic table, for instance, and you look at sodium, which is Na, you're going to see 2 numbers associated with it. And we talked about the first number already, right? This one here is the atomic number, or the number of protons. But now the number underneath, right, that number is known as the atomic mass or the atomic weight. And what that represents is the weighted average of all the naturally occurring isotopes for that element. Right, so you want to keep in mind that this is not the same as the mass number. Right, we represent the mass number and the number of protons using our atomic or nuclear symbol. This here is just what we actually see on the periodic table. So this number underneath, which is usually a decimal number, is going to represent the atomic mass or the atomic weight, which is the weighted average of all the naturally occurring isotopes for that element, right? And what we're going to see is that the isotopes, we don't have an even amount or equal amount of those for the different elements. They actually exist in different abundances, or different percent abundances, right? So one isotope may be more prevalent than another isotope. So that weighted average that you see on the bottom actually takes that into account. So it relies on the fact that one particular isotope may be more, make up more of a particular sample than another type of isotope. All right, so if we use our periodic table, we can then identify what the atomic mass of each of the elements are on our list here, for instance, right? So if we take a look at a couple of these, we can look. So if you look up calcium on the periodic table, right, what you'll see is the following. You'll see Ca, right? You'll see it has atomic number 20, and then underneath you'll see 40.078, depending on the table that you see. So the atomic mass here is the 40.078, right? So that's the average atomic mass or the average atomic weight for calcium. And the unit for this is the really small unit of the atomic mass unit, or AMU. All right, so you can look up in your periodic table the atomic mass of each of these elements. So we said that isotopes are just different atoms of the same element that have the same atomic number but different numbers of neutrons, which makes their mass numbers different. Most of the elements on the table are going to have two or more isotopes that contribute to the overall atomic mass or atomic weight of that particular element. So for instance, we'll just pick a couple of these. So lithium, for instance, has two isotopes, lithium-6 and lithium-7. And what you'll see here is the atomic mass, right, for lithium is actually 6.941. So it's closer to 7 than 6. And what that means is that lithium-7 then is more abundant. Right, so because there's just more of that particular isotope in the sample, it will contribute more to the weighted average mass. So the weighted average then is a lot closer to 7 than it is to 6. Similarly, if we look at copper down here, right, we can see that copper exists as two isotopes, copper 63 and copper 65. Well, the weighted average of those two isotopes is 63.55, right, which is closer to 63 than 65. And this then, we can use that to deduce that copper 63 is the more abundant isotope. Because the atomic mass is closer to 65. Is closer to 63 than it is to 65. So we can make some pretty sound conclusion just based on what we see on the periodic table and if we know the different isotopes that are present. So here's another example of one of these. So chlorine, for instance, exists as two isotopes, right? We have chlorine 35 and we have chlorine 37. All right, so when we look at the weighted average, the atomic mass from the periodic table, we see that that weighted average is 35.45, which is a lot closer to 35 than it is to 37. So we can conclude then that chlorine 35 is more abundant. There is just more of it in a sample of chlorine than the chlorine 37 atom. All right, and then the last one here, we're told that lithium has two naturally occurring isotopes. I believe we already addressed that one when we looked at our table up here at the top. So because the weighted average here is closer to 7 than it is to 6, we can say that lithium-7 is the more abundant isotope. All right, and remember the atomic masses, we get these just by simply looking them up from the periodic table. So far we've taken a look at how we represent the number of subatomic particles, and we've been focusing mostly on the protons and neutrons. Now we're going to change our focus and look at the electrons. Because as we'll see down the road, and as you've already seen in lab, the electrons are the things that are going to dictate how a particular atom behaves. So before we get to that point, let's first of all take a look at what's known as electromagnetic radiation, which we often abbreviate as EM radiation. And this type of radiation includes things like radio waves that you're being exposed to all the time, microwaves in your microwave oven, the light that you see on a regular basis, and other types of radiation like X-rays that you would be exposed to at the doctor's office, for instance. So the thing to keep in mind about your electromagnetic radiation, including the light that we see, is that they're composed of particles that move actually as waves of energy. And if they move as waves, there are some relationships that we can come up with. So if we were to draw a wave along an axis like this, right, then our wave can look something like a typical wave you would associate with. So it goes like that. And there are a couple things that we can identify from the wave. The first is something known as the wavelength, or the length of the wave. And that is simply the distance from one peak to the neighboring peak. Right? So this here is called the wavelength of this particular wave. It's also the same distance from one trough to the other trough, or the bottom of the wave. Essentially what it is just a distance from one point in the wave to another point that's equivalent. So this would be a wavelength as well in our particular wave. So different waves, like radio waves, microwaves, visible light, etc., will have different lengths of their waves, or different wavelengths. And these different wavelengths are associated with different energies. So on the electromagnetic spectrum, we can see several of these different waves and their associated wavelengths. So for instance, we can see on the left side of the spectrum here, we have something like our radio waves, which have pretty long wavelengths. And on the other end of the spectrum, we have things like our gamma rays and X-rays, which have really small or short wavelengths. And what you'll notice right underneath is the amount of energy associated with these different wavelengths. So a short wavelength has high energy, and a long wavelength has low energy. So we can say then the relationship is, as the wavelength decreases or goes down, the energy increases or goes up. Right, so shorter wavelengths have higher energy, like in this region of the spectrum, whereas longer wavelengths have a lower energy. All right, and this is a really good diagram that shows you all the different types of electromagnetic radiation, and the fact that the visible light that we see on a regular basis with our eyes only makes up a very, very small part of that spectrum. But within it, we can see all the way from red light, which has a wavelength of about 700 nanometers, to blue light, which has a wavelength of about 400 nanometers. Right, so now, because of the difference in wavelength, we can say now, because red light has a longer wavelength, it is going to have a lower energy. And then blue light has a shorter wavelength, so it's going to have higher energy. So in other words, the color of light corresponds to the energy associated with that particular color. So when you subject an atom to different energies, so for instance, if you have a source or an atom or a sample of something and you heat it, or you subject it to an electric current, what happens is that that thing starts to glow and it starts to give off light. And if you pass that light through some sort of a prism, right, then that light gets broken down into its component colors. And we can see that those colors shown here for that particular sample or atom in what's known as an atomic spectrum. And you can think of that spectrum, these lines here, as sort of like a fingerprint for that atom. In this case, it's barium. And we can use it to identify what that particular atom is. Now, the reason why we're going to see these lines exhibited here on the spectrum is because those lines are associated with the change in energy of the electrons in those particular atoms when they get exposed to some sort of energy. And each electron in a particular atom has a specific energy level or shell that it belongs to. And these shells or energy levels there's a fancy word for them. We assign them values called the principal quantum number. And again, it may seem complicated, but we just use an abbreviation N to represent that. So the shell or the principal quantum number or the energy level can be represented as N equals 1. That's the first energy level. All right, so N equals 1 equals the first shell. N equals 2. This is the second shell or second energy level. N equals 3 is the third energy level or the third shell. N equals 4 is the fourth shell, etc. Right? So it's pretty simple. The N value just tells us the energy level or the shell that we're dealing with. Now, as the value of N goes up, the energy of that particular shell increases, and the distance from the nucleus increases as well. All right, so we can say then that as N increases, the energy also increases, and the distance from the nucleus also increases. So it's a straightforward relationship between what N is, the energy associated with it, and the distance from the nucleus. So these different energy levels correspond to different distances from the nucleus and different energies as well. All right, so if we were to think of our nucleus as down here, right, N equals 1 is the lowest energy level, and then out of this here, N would be the highest energy level, and this N equals 5 will also be furthest from the nucleus. Whereas N equals 1 would be closest to the nucleus, right? And remember, the nucleus is right here. I just wrote all over it, but that's where our nucleus is. So these energy levels then are known as quantized energy levels, meaning that they contain specific amounts or packets of energy. There is no in-between level. All right, so you'll notice here that there's an N equals 1 and an N equals 2. So an electron that is in those energy levels can only be in these steps here of or in these shells of our bookshelves. There's nothing in between where that electron can reside. And that essentially is what quantized means. So what happens when an electron is subjected to energy? So if an atom is subjected to energy, that energy could be heat, it could be electricity, for instance. Doesn't really matter the form of energy that it's exposed to. The electrons will absorb that energy and they become excited, is the term that we give to that. As a result, they will jump to a higher energy level. So that's shown over here, for instance. So this electron is jumping to a higher energy level. And then eventually what can happen is that electron can eventually fall back from where it came from. So fall back down to a lower energy. And we say that it relaxes. And when it does that, when it goes from a high energy now to a lower energy, it is going to give off that energy in the form of light. So energy released as light. And the color of the light corresponds to, now we know the energy associated with each color. So the color of the light corresponds to the energy given off. So for instance, if we see green light, right, that means that more energy is given off than if we see something like red or orange light being given off. Right, so the color that we see is indicative of that. And that may seem, somewhat far-fetched, but we actually see examples of that all the time, right? So for instance, fireworks. The different colors that you see correspond to all of those electrons falling back down and relaxing and giving off their energy in these different colors that you observe, right? So if you see blue fireworks, that means that particular substance is giving off a lot of energy. You see red fireworks, it's giving off a lower amount of energy. All right, so if an electron moves from the first energy level to the third energy level, right, so it goes from n equals 1 to n equals 3. It goes from a low energy to a high energy. That means energy is absorbed, right? So it'll be similar to this example that we showed here. If an electron falls from the third energy level to the second energy level, so it goes from the third energy level would be n equals 3 to the second energy level n equals 2. Right, it's falling down. That means energy then would be released or emitted. And if an electron moves within the third energy level, so it stays in the n equals 3, right, because there is no change in the energy level, then the energy here is not going to be changed. So no change in energy. So when it comes to organizing our electrons in these different shells, we can actually use the periodic table to help us in this process. So we've seen in lab that the periodic table can be used to help us predict, the ions that are formed, and we'll see that in the next chapter. But the periodic table can also help us to predict how the electrons are arranged in these shells in a particular atom. We just have to be able to interpret what the periodic table is telling us. And we're just going to limit ourselves to the first 20 right now elements. And the first thing to note is that the period number actually tells us the shell. And again, the shell is just the same as the energy level or the principal quantum number. Or the principal energy level, I'm sorry. All right, so we use all of those terms, I apologize for the scrolling, to represent these shells or these energy levels. So the period number then is going to tell us. So this here, all of these belong to, in period 1, they belong to the first energy level. So hydrogen then only has one electron, right here. So there's my hydrogen, atomic number 1, so 1 electron, and the only place for that electron to go would be in that first energy level. So it'll have an electron arrangement of 1. Helium is the second atom on the table, and it still belongs to the first energy level. So for 2 electrons, like helium, the electron arrangement will be 2. So your first period, which is the first energy level, can only accommodate 2 electrons. So first energy level, which is the first period, can only accommodate 2 electrons. Then we go to the second period, and we can see that it goes from lithium all the way over to neon. So lithium then, or before we get to lithium, the second energy level, which is the second period, you'll see it goes 1, 2, 3, 4, 5, 6, 7, 8. So it can accommodate 8 electrons. So lithium, for instance, right, when you have to do your electron arrangement, you always start at the top and work your way across until you get to the element in question. All right, so we're going to start at the top here. We go 2 all the way across, and then 1. So lithium will be 2, 1, and that tells us that there are a total of 3 electrons in lithium. Beryllium is right next to it, and beryllium has 4 electrons. So we start at the top, we go across 2, and then beryllium, we end with 2 more, and that's 4 electrons. Boron is over here. We start at the top, we go 2, and then we go 1, 2, 3 to get to boron, and that's a total of 5 electrons. Carbon is right here. We start at the top again, we go all the way across, 1, 2, and then to get to carbon, we go 1, 2, 3, 4. So 2, and then 4 to get to carbon, right? And we can do that for all of the elements on the periodic table. Let's jump to neon right now. So there's neon right here, right? You can see neon has 10 electrons. We're going to start at the top. We're going to work our way across. So 1, 2 gets us to helium. And then 1, 2, 3, 4, 5, 6, 7, 8 gets us to neon. And those are our 10 electrons. Right, then we get to our third energy level, which is the third period. And if you can see, also the third energy level has 1, 2, 3, 4, 5, 6, 7, 8 electrons that it can accommodate. So if we choose something like, I'm going to erase some stuff here. If we choose something like chlorine, all right, so chlorine would be right here. Right, so we know that there's 17 electrons that we would have to arrange. Well, we start at the top, right up here, and we work our way across. So 1, 2, then 1, 2, 3, 4, 5, 6, 7, 8 gets us to neon, and then 1, 2, 3, 4, 5, 6, 7 gets us to chlorine. So that's 8 into 10 and 7, 17. Those are 17 electrons for chlorine, and we can use our periodic table to help us.